Okay, AP Stats, here we go with Chapter 9, Section 9.1 explains what a significance test is. There are two kinds of inference procedures in statistics. One is a confidence interval. The second one is the significance test. So we already have talked about a lot of the idea behind it. All right. It's all of the do we have good evidence type conversations. That's leading into the significance test. All right, here we go. If I claim to be a 94% free throw shooter, and then I go out and I make 8 out of 20 free throws, you would probably claim that I'm a little too full of misses. You see what I did there? Because you thought I was going to say full. Okay. So anyway, but you should back up your argument with numbers. That's the thing. If I go out, I say I'm 94%, and I go shoot 8 out of 20, that's 40%. It's really good evidence that that's not true, right? Good evidence that that's not true. But there's got to be a line that we draw. You should back up your argument with numbers. What's the probability that I'm actually a 94% free throw shooter and I actually do, like, what's the probability I'm actually a 94% free throw shooter and I go out and I shoot 40%? That's the idea of the significance test. You base this claim as if it were true and find the probability that this happened. That's a significance test. Well, 20 times 0.06, 20 times 0.06, you see what I'm doing? Q is 0.06, is equal to 1.2. Is the sampling distribution of p hat approximately normal here? No. So that's a little trick from chapter 7, right? This is what I did right here was n times q. If n times p and n times q are both greater than 10, I can say p hat is approximately normal, and I could find a probability with the normal CDF. But because n times q is less than 10, we're going to use a binomial CDF. We're going to go back to chapter 6 to answer this question. What's the probability that x is less than or equal to 8? What's the probability that if, I can't stress this enough, if 94% is true, you have to keep that along for the ride. Hey, let's just say 94% is true. Let's find out the probability to make 8 or less. Okay, so it goes like this. The probability that x is less than or equal to 8. I'm going to draw this out a little bit because you haven't seen it in a while. You got a final exam coming up, right? Look what I'm doing here. The probability that x is less than or equal to 8 is equal to these separate probabilities put together. They're all mutually exclusive, so I can add them together. Now I'm going all the way back to chapter 5. And so I'm going to write this as a binomial CDF, and that went n, p, and x. So 20 free throws. Look what I'm putting in for the p. I'm putting the thing that was actually claimed, and then I say 8. And the calculator gives me 1.74 times 10 to the negative 10. You know, on the calculator, it gives you that E and then negative 10. So look, that's, I got to move this 10 places. I move across the one, then there's 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 7, 4. That's the probability that a 94% free throw shooter would go 8 for 20. That probability is so low that it speaks volumes. This probability says there's no way that would happen if that was true. So this is convincing evidence that that is not true. The idea of a significance test is that we work on the assumption that we're told, whether we believe in it or not, and we find a probability that we get the data we got, all right? The idea of a significance test is that an outcome, like an X bar or a P hat, this 8 out of 20 is a P hat, isn't it? Right? That would rarely happen if a claim were true. The fact that it happens is good evidence that the claim is actually not true. Okay, before I go on, I want you guys to take a look at that sentence again. The idea of a significance test is an outcome that we get from data that would rarely happen if a claim is true. That outcome is good evidence that the claim is not true. So here's your definition. A significance test. A significance test is a formal inference procedure in statistics. It's your second inference procedure. For comparing observed data, that would be an X bar or a P hat, right? With a claim about the population. Like I'm a 94% free throw shooter, right? The claim is always a statement about a parameter. When I say I'm a 94% free throw shooter, I'm referring to a population proportion, right? So I'm a 94% free throw shooter. That's my claim, right? That's the claim. That means the parameter is P equals 0.94. That's the suggestion, right? Then we go and we do a sample and we get data and we find what's the probability I would get data that far away from this 94% if that was actually true. All right, so to set this thing up, you're gonna need a hoe, you're gonna need a ha, and eventually a couple pages from now we're gonna need a Jesus fish. A hoe, a ha, and a Jesus fish. That's what we need for a significance test. Get ready, it's gonna be a ride here. Go to page 2. A null hypothesis, which I will refer to exclusively as a hoe in this classroom, is technically read H naught, H sub O, H naught. I'm going to call that a hoe every time. That's the claim about the population parameter. It's always about a parameter. For example, I'm a 94% free throw shooter, would look like this. The null hypothesis is P equals 0.94. That's how we write it up. The hoe is that the parameter proportion is equal to 0.94. An alternate hypothesis, H sub A, which I will exclusively refer to as the ha in this class, is the hypothesis that the parameter is something other than what is claimed in the null hypothesis. For example, Larson, you're much less than that. You are not a 94% free throw shooter. You're less than that. We don't give an alternate number, right? So I want to say ha is never an alternate number. It's just saying that we don't think what you're saying is true. What is true, we think is either less or maybe greater than, or sometimes we just say not equal to. All right, so I'm going to go to an example in the book. Page 555, got the book right here, Juicy Pineapples. Stating hypotheses. At the Hawaii Pineapple Company, managers are interested in the size of pineapples grown in the company's fields. Last year, the mean weight of the pineapples harvested from one large field was 31 ounces. A different irrigation system was installed in the field after the growing season. Managers wonder if this change will affect the mean weight of pineapples. So it was 31. That's going to be the claim. It's not always something we claim is true. It could be something that used to be true. So we're going to put it as if we're claiming it's still true, and we're just looking to see if it's different. So the alternate hypothesis would be it's not 31 anymore, it's different, right? A different irrigation system was installed. Managers wonder if this change will affect the mean of pineapples grown in the field this year. Now, it didn't say greater than, it didn't say we want to see if they're bigger or smaller. We want to see if it just affects the mean. So state the appropriate hypotheses. Here we go. The hoe is that mu equals 31. This is a mean problem, not a proportion problem. So the mean of the population is 31, and the alternate is just that it's not 31. We want to see if it's different. Okay, that's how those go. And so the hoe, for number 1, I don't understand why there's a 1. Oh, let's check your understanding. I see what's going on. So the next thing is flip the page, and we're going to write some appropriate hypotheses. Here we go. It'll take a minute. For each of the following settings, state appropriate hypotheses for performing a significance test. All right, according to the National Sleep Foundation, 85%, that's a proportion, not a mean, 85% of teens are getting too little sleep on school nights. Janie, I guess that's what she's spelling there, wonders whether this result holds true in her large high school. She asks an SRS of 100 students at the school how much sleep they get, and 75 out of that 100, that's 75%, are getting less than the recommended amount of sleep. So our girl Janie actually has a direction. She thinks it's less than the population proportion. So my hoe is that P equals 0.85. That's a population parameter that P is equal to 0.85. The ha, I'm not going to say anything about P hat here being 75. I'm going to say that P is less than 0.85. You see what I mean? We put a claim, And then we just kind of suggest that the claim isn't true, and we might give a direction, but we don't give an alternate number. We don't even say anything about p hat at all. We are finding results about the population parameter. We use the p hat in order to get a probability, to say stuff about the population parameter. But as far as the ho and the ha, the hypotheses are concerned, we just talk parameter. Number 2. Here we go. As part of its marketing campaign for the 2010 census, the U.S. Census Bureau advertised 10 questions in 10 minutes. It's all it takes. On the census form itself, we read, the U.S. Census Bureau estimates that for average household, this form will take about 10 minutes to complete, including the time for reviewing the instructions and answers. We suspect the time it takes may be longer, so there's a direction on this one also. Please note, this is about means, right? The average household. This is about means. About 10 minutes to complete. So our ho here is that the mean is equal to 10 minutes. We should usually have some units of measure along with stuff in these hypotheses. And we believe it's going to be longer, so we're going to say greater than 10 minutes. All right, that's how you write a ho and a ha. So we figure out the ho and a ha. Never forget this in this class. Never forget this. The ho and the ha must always be written as parameters. Always as parameters, not statistics. The ho and the ha have nothing to do with data. They're comments about the parameters. So what are we using for this? We're using mu or p primarily in this class. Now, before we get to this Jesus fish, we got to find a p-value. There's the terminology for the statistics test. On the assumption that the ho is actually true, like that 0.94, right? Okay, let me assume that's true, and I'm going to do a normal CDF with 0.94 as my mean. On the assumption that the ho is true, the p-value is simply, it's no big deal, it's just the probability that we get a statistic. It's the probability that we get a statistic as far away from that ho as we did when we took our sample. What's the probability that we go 8 out of 20 when we say 0.94 is the truth? That's the idea, right? So the p-value is a probability. So in chapter 7, when we did sampling distributions, the big questions there were find the mean, find the standard deviation, and then I asked you probability questions. And you did normal CDFs to find them. Well, that was a setup for this right here. You finding this probability is a direct result of what you learned in chapter 7. Okay, why would this evidence the sample mean, so I'm going to put X bar there, or proportion, the stuff that we get from our data, why would this evidence be so convincing? Okay, for the free throw example, there are really only 2 possible explanations for getting the sample as far away from p equals 0.94 as the p hat of 8 out of 20, which is equal to 0.40, by the way, that we got. We're claiming 94%, we got 40%. There's only 2 possible explanations for why that happened. The first one, the players claim the ho is actually true. I mean, that's possible, and he or she had some very, very bad luck when obtaining that sample. Or, especially in a scenario like this, when the probability, the p-value is really, really small, the players claim the ho is false. It's just not true. Or it's no longer true. It's something that used to be true but isn't true anymore. That's probably not the case for the free throw thing, but maybe more the pineapple thing. It used to be 31 ounces, but we changed our game here on how we're farming, and now it's no longer true. What's almost certainly true, let me use a word here, convincingly, because we've been asked over and over, do you have convincing evidence, right? The player's claim is false. It's no longer true. What's almost certainly true is that the shooter's percentage is less than 0.94, which would be the ha. So when we make a conclusion about this test, we want to favor the alternative hypothesis. We don't want to say what we think the new number is. We just want to conclude, yeah, you're not a 94% free throw shooter. It's less than that. See what I mean? Okay. Moving on to page number 3. So if it's called a significance test, what are we trying to do? In every test you do for the next 3 months, you're looking to see whether the data that you found, the X bar or the P hat or whatever it is, gave enough evidence to reject the hoe. That's what we're looking to do with this significance test. We're rejecting hoes, people. If the p-value, the probability that the statistic would be that far away, is small enough to be sure that the hoe is false, we conclude our test by saying we reject the null hypothesis. Reject the hoe. The second one, if the p-value is not small enough to be sure that the hoe is a fake hoe, then here's how we conclude our test. We fail to reject the hoe. So our last sentence is either rejecting a hoe or failing to reject a hoe. That's it. The last sentence is all about the hoe. We never, ever, ever accept a hoe in this classroom. We either reject a hoe or we fail to reject a hoe. We do not conclude that a hoe is a true hoe. We reject a hoe or we fail to reject a hoe. We don't prove that a hoe is true. We never do that in this class. Now, how do we measure evidence against the hoe to decide whether or not to reject the hoe? What kind of probabilities, p-values, would lead us to reject a hoe? Okay, so we get data like a p-hat. We put the hoe, like the 0.94, in the middle of our sampling distribution. Call it the mean. And then we take the p-hat and we find the probability that p-hat would be that far away or further. We shade in the normal curve. We'll talk about this in section 9.2 and 9.3. But once we do that, we find a probability. So here's the breakdown. Small p-values, a small shaded section, the small probability of getting 4 out of 20 or 8 out of 20 when you're a 94% free throw shooter. Those are good evidence against the hoe because they say that the result we observed wouldn't happen very often if the hoe was true. So therefore, we conclude the hoe isn't true. The second one, tiny p-values, like the one we got. I put Timmy. Tiny p-values are great evidence against the hoe, like the 0.0000000000173 we got. That's great evidence against the hoe, because they say the result we observed when we took our sample, that would be almost impossible if the hoe were true. So, reject the hoe. Damn sure reject the hoe. And then the third one, larger p-values. Those are poor evidence against the hoe because they say the result we observed could actually happen if the null hypothesis were true. So this would be the scenario where we fail to reject. Of course, remember, you never, ever, ever accept a hoe in this classroom. You reject a hoe or you fail to reject a hoe. We do not prove that hoes are true. All right, here's an example I'm going to leave you guys to read that. The problem gives you a p-value, and then you decide whether or not you should reject or fail to reject. Okay, how much evidence do we need? I'm going to move on here. We have picked an arbitrary cutoff number that it really does come from common sense, and we've had this common sense conversation. An arbitrary cutoff for the p-value. When is the probability small enough for us to say, yep, I'm going to reject that hoe? We give it the variable alpha. That's the Greek symbol alpha. I will probably call that a Jesus fish, even though I know that's slightly insensitive. Most of the time, we stick with alpha equals the number you guys have come to know, 0.05. But for some problems, we may be told to use a different one, like alpha equals 0.10 if we're not in the need of really great evidence. Like, getting a 0.08, that's not smaller than 0.05, but if we're just looking to make a change and say, yeah, let's reject that hoe and move on, then 0.10 is good. Or maybe alpha equals 0.01 Whoa, that was a sneeze that came out of nowhere. Now you have to say bless you out loud. Go ahead. Okay. If we want to be really sure before we reject the null hypothesis, maybe the result of us doing this test is giving a recommendation, and maybe it costs a lot of money to change something. You know, like they put in a whole irrigation system in Hawaii for those pineapples. That's got to cost money, right? Well, before we go rejecting a null hypothesis, and the result means we got to change something, it costs a lot of money. Maybe you want to have really good evidence, so you make this smaller and smaller, so it's harder to reject the null hypothesis. You need really, really good evidence to do so. All right? Alpha, or the Jesus fish, is called the significance level for the test. Significance level. 0.05 is the one we landed on for the most part. All right, going on to the last page of notes here. Yeah, there's a write-up that we're going to have to do for this whole thing. Just like with the confidence interval, we're going to do a write-up. You got to name. See, I told you it was repetitive. Look, a lot of this is stuff you've already written. So, you know, you already have at least a C+ on this thing before even learning anything today. Name the population of interest. Name the parameter, but it's not something we're going to estimate now. We don't offer what we think is true. We either reject or fail to reject something that they said was true, a claim. So we're going to name the parameter that we will draw conclusions about. You see how that's different? Okay, then we'll name the procedure. It'll be called either a one proportion z-test, or it will be called a one sample t-test. Now the author has moved on from this one proportion stuff and sometimes refers to it as a one sample z-test and a one sample t-test. I can explain that just real briefly. Next chapter 10, we're going to run into two samples so we can compare two different populations. Right now we're just dealing with one population at a time, so we call it a one sample z-test or a one sample t-test. State the hypotheses. I typed this wrong. Sorry, guys. Declare the significance level. Sorry, I rewrote this earlier today and I screwed it up. Alpha, and then you don't need this part. The condition random, same exact condition independent, same exact condition normal. You already know how to do that. Calculate a test statistic and calculate a p-value. You know what I'm going to tell you we're going to do? We're going to do this with a z-score, and we're going to do this with a normal CDF. That's what the next two sections are about, making sure that we get that right. Okay? You can reject or fail to reject a hoe. You do not accept a hoe in this classroom. Explain the result in context. Don't forget to finish by answering the actual problem you were asked. Okay? Here's how rejecting or failing to reject should be written as the last part, right? Number 11. You had to interpret a confidence interval. We had to learn how to do that. Now we've got to learn how to write our last sentence of this test. Okay, it goes like this. With a p-value, I'm going to make something up here. With a p-value of p equals 0.03, clearly less than 0.05, we find that the data is statistically significant. Statistically significant to reject that hoe. And conclude with context, make sure that you explain the problem, that the alternate hypothesis is likely to be true. We don't replace a number with a new number. We just say we think it's less than you said it was, or we think it's not equal to what it said it was. All right, failing to reject. With a p-value, I'm going to make up another one here. With a p-value of p equals 0.19, clearly bigger than 0.05. The data is not statistically significant, so we fail to reject that hoe. Now keep in mind, that doesn't mean that we proved that the null hypothesis number is true. We never do that. We just fail to reject. It's kind of like this. If somebody's on trial for a crime, and we go through the lawyers, and then you go through the jury and all that stuff, at the end, what happens? You either find the person guilty, or you find that they're not guilty. You don't actually know the truth in the end, right? You don't actually know the truth. You just found them guilty or you found them not guilty. That's kind of the result here as well. Never, ever, ever say that the hoe is correct. We never say that we found a true hoe in this classroom. We reject fake hoes, but we don't find true hoes. That's accepting a hoe, and that's not allowed in this classroom. All right, I think it's worth your time to read that example also, and then there's some homework for you guys to do in the book. Have yourselves a great day. We'll talk more about section 9.1 tomorrow.